I shall continue with the Pythagoras Theorem. In this method, I shall explain how to prove it using algebra. Now, to start off with, we draw the same figure that we have seen using the rearrangement method. Okay, so that means we have a big square, not a very nice square. Okay, with and I fit 4 of these triangles into it. Okay, so that's B, A, B, A, B, A, B, A, C, 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 C. Okay. Now then, I shall write down the area of this big triangle in terms of A, B, and C. So there are 2 ways, or at least 2 ways we can do this. One way is to just look at this side, which is made up of A plus B. So therefore, the area of this big triangle in terms of A plus B would be just A plus B squared. Another way is to add up the separate figures inside the square. That smaller square has an area of C squared. Now, each of this triangle would have an area of half base times height. So that's half times A times B. Half A, B. But there are 4 of them, so this will be multiplied by 4. So the total of these 2 should be equal to A plus B squared. Since together they make up the big triangle. And if we simplify this, we would get the Pythagoras Theorem. Let's try. A squared plus 2AB plus B squared is what we get if we expand A plus B squared. That's C squared plus half times 4 is 2. So this is 2AB. Now, I can subtract 2AB from both sides. And now, we have the Pythagoras Theorem. Okay, we're left with A squared plus B squared equals C squared. So that's proving Pythagoras Theorem using algebra. Now let's look at another method. In this method, we shall use similar triangles. So let me start with right-angled triangle. That is the right angle. Now, I shall drop a perpendicular from this corner to the longest side. So that's a right angle. I notice that this angle here is the same as this angle. Okay. Now, to make sure we understand why, let's think about this angle here. This angle here would be 90 degrees minus theta, and then we need to check whether the sum of those three triangles, if that's the theta, we need to check if this plus this plus this is 180 degrees. And if I add those two, the theta and the minus theta cancels, and we have 90 plus 90, which is 180. So that's correct. So this is theta. Okay, so this means that this triangle is therefore similar to this triangle and similar to that triangle, because all the angles are equal for this big triangle, this smaller triangle, and the smallest triangle. So they're all similar. So let me label this a bit. I'll call this A, B, C, and I'll call that D. Now, consider the ratio of these two sides. BC, no wait, the AB over BC. So this ratio and that should be equal to, if I then look at this triangle, the corresponding sides would be BD over BA. And since these are corresponding sides, the two ratios should be equal. Next, let's look at the ratio between this side and this side. So that's AC over BC. AC over BC. The shorter side divided by the longest side. And then let's look at that similar triangle. Corresponding sides would be, that's the shortest, that's the longest. Okay, so it would be CD over AC. So they should be equal since these are corresponding sides. Now, let's rearrange this. AB and BA are the same. So that's cross multiply to give AB squared on one side and BC times BD on the other side. Similarly, let's do the cross multiplying here to get AC squared equals to BC plus CD, times CD. Now let's see where we are heading. AB is this. So now we have this side squared. AC is that. So we have that side squared. Okay. So since Pythagoras theorem is about the sum of the two shorter sides, let's add these two up and see what happens. AB squared plus AC squared is equal to BC times BD plus BC times CD. Now let's BC is a common factor, so let's factor those out. This gives BC times bracket BD plus CD. Okay. Now BD and CD are here. That's BD, that's CD. So the sum is therefore BC. BC times BC, which is just BC squared. Okay, so if we call this A, for example, and call that B, this side B, and call this side, oh, wait a minute. So conventionally, I should call this letter C, since it's opposite to the corner big C. And if I call that side A, then in this simpler notation, AB would be C squared, AC is the B squared, and BC is A. So A squared. So now we have once again proven the Pythagoras theorem. Okay. Now the final method I shall look at is using differentials. Now this method would be conceptually more difficult because it uses calculus, and you would really understand this only if you have learned calculus, if you have learned how to differentiate and integrate. Alright, if you haven't, then just have a look anyway and see what you think. So let me start with right-angled triangle. I'll call this side Y and call this side X. That's the right angle. And I'll call this side A. I'll label this A, B, C. Now consider what happens to Y if the side X increases by a little bit. So X increases by a little bit. Let's call that little bit dx. So dx is a small increase. And that's what this differential means. Differential in the sense of a small increment. So if I now draw the new y, it will look like this. Obviously, y is now a little bit longer. But how much longer? Well, approximately we can draw a perpendicular from that point to this line. Okay, and this side would be approximately the increment of the side y. So y would have increased by that amount. Now, strictly speaking, I should really draw a circular arc there, centered at this point. Okay, then these two sides would be equal, and then that side would be the increase in y. But because the dx is so small, this angle is really small, and drawing a circular arc or perpendicular line would be approximately would give approximately the same dy. So this is the kind of arguments that we use when we deal with small changes. Okay. Now, let's look at this tiny little triangle. Now I'm going to call this side E and that side F. Okay, I hope you can see that. Now, and notice that this little triangle is in fact similar to this bigger triangle. Because if that angle here is theta, then this angle here is also theta. Now, to see why this is also theta, let's see. Now, when the increment is very small, this angle here is also approximately 90 degrees. So those two are very close to 90 degrees, which means that this is actually very close to 0. Okay, now so it probably doesn't make sense if you want to be very rigorous about this. But for a very small change, this would be approximately correct. Okay, because after we have set up all the equations, we are going to have to take the limits when both dy and dx goes to 0. Okay, then those two angles would actually go to 90 degrees. When we do that, then everything becomes accurate. So for now, all these are approximately correct for a start. So that angle will be theta if that's 90 degrees. Okay, because the sum of those two angles is equal to the sum of those two angles. That's the simple reason, since that's the exterior angle from that line to that line. Okay, so we have this connection here that the triangle ABC is similar to the triangle ABC. So that goes from the sharp corner to the right angle and then to C. And here the corresponding sides would be, right, that's the sharper corner of this tiny triangle, that's the right angle. So it goes from C to F to E. Triangle CFE is similar to triangle ABC. Alright. So Let's take the ratio of the corresponding sides. Let's take dy over dx. So let's take this ratio. Now dy is the shortest side, dx is the longest side. So this would correspond to, for the bigger triangle, to those two sides, the shortest side over the longest side, x over y. So now we have an equation, a differential equation with the dy dx, and we can actually integrate this. Let's try that. We can do something like cross multiplying. So y goes up there, dx goes up there. After that, we can integrate it. Now to integrate this, we need to put in the limits. So that's the thing. Let's do the special case. Okay, let's not put in the limits. Let's do it the other way. Let's treat this as indefinite integrals, so that when we integrate it, we would get an unknown constant. So if we integrate y by dy, we'll get half y squared. X by dx gives half x squared. And then we get this unknown constant, big C. And now we put in the possible values for x and y. Now, if we just look at this triangle, x and y can represent any values. It's supposed to be general. But for the special case, if when x is 0, let's imagine that we reduce this side so that this side gets shorter and shorter until x becomes 0. So when x is 0, y would then coincide with this side, because if this side comes down to 0, the triangle collapses and y just falls flat on the side A. So y is equal to A. So that means we have this relation, connection, that when x is 0, y is A. So we can substitute this into the equation. And this gives us a way to find C. In fact, we've just found it. C is equal to half A squared. Now let's substitute C back into this equation. I get half y squared equals to half x squared plus C, which is half A squared. Now let's multiply both sides by 2 so that the halves cancel. And we are left with y squared equals to x squared plus a squared. So that's y squared, that's the longest side. A and x are the two shortest sides. And therefore this is the Pythagoras theorem. So that's it. We'll stop here.